Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS Weather Talk webinars. Thanks for joining us today. I'm your host, Henry Regis. Behind the scenes, running the technical side of our program, are Zach Schwalbe and Noah Newman. We're coming to you live from the Colorado Climate Center here at Colorado State University in Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we'll be recording this broadcast today for future viewing on our website. All of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today's webinar will focus on the hydrologic cycle and how river forecast centers measure its parts. We're excited to have with us today the North Texas Regional CoCoRaHS Coordinator and Hydrometeorologist for the National Weather Service's West Gulf River Forecast Center in Fort Worth, Texas, Greg Story. Greg has been with the River Forecast Center for just a little over 20 years. Greg is the president of the North Texas chapter of the American Meteorological Society and the National Weather Association, and an avid Texas Rangers baseball fan. Welcome, Greg. It's a pleasure to have you with us today.
Well, thank you very much, Henry. It's good to be here. I'm excited about the opportunity that I have to speak to everybody. I'm quite aware that there might be a large number of people who are not real familiar with what the river forecast centers do in the National Weather Service, and so if nothing else, I hope that the opportunity avails itself and people learn a little bit more about what river forecast centers do within the National Weather Service. So our focus today is going to be on the hydrologic cycle and how it relates to river forecast centers. And specifically, we're going to talk about how do we measure its parts. There are different aspects to the hydrologic cycle. Some we know a lot about, and others we know very little about. So just to give you an overview of what we're going to be talking about over the next 45 minutes or so is, firstly, as I mentioned, we're going to talk a little bit about what the mission of a river forecast center is within the National Weather Service. Next, we're going to talk about the hydrologic cycle, what can be measured directly and what cannot be. You've all filled out a little bit of a quiz survey when you signed up so that I could get some idea of how familiar you are with what we can and cannot do in terms of measuring the hydrologic cycle. And next, we're going to talk about what hydrometeorologists do at a river forecast center. And of course, we'll be using the West Gulf River Forecast Center as a primary example, since that's where I've worked since the end of 1993. And the bottom line is that we're going to be talking about is we need more CoCoRaHS weather observers for the purposes of filling in one part of the hydrologic cycle, and that is measuring precipitation. Just to give you a little bit of a background that I have, I graduated from Northern Illinois University with a degree in meteorology back in 1976. Northern Illinois, for those not familiar with us, is about 70 miles west of Chicago in DeKalb, Illinois. I was a broadcast meteorologist after graduating from college for 14 years. Spent a couple of years up in Green Bay, Wisconsin, and 9 years in Cedar Rapids, Iowa, just to name a couple of my stopping points. And in a way, doing this presentation today makes me feel like I'm back in broadcasting in a way, because I'm talking into a microphone and I'm not seeing my audience. It reminds me of my days when I used to talk to a television camera or speak into a microphone for broadcast purposes, and you have no idea if anybody is out there or not. You can't see them, you can't hear them. I'm going on the assumption that you're there and that you'll benefit from what I'm talking about today in this webinar. I joined the National Weather Service in early 1990 and was a meteorologist intern in Shreveport, Louisiana for nearly 4 years, and I've been with the National Weather Service West Gulf RFC in Fort Worth, Texas since November of '93. I'm a hydrometeorologist. For those not familiar with our terminology, that means I'm a meteorologist that deals specifically with the things that influence hydrology, that being flooding, water supply issues, and drought. So that's a little bit about what I do. So as a hydrometeorologist, it is my responsibility to determine how much rain has fallen in the past, how much rain or snow is occurring right now, and how much is going to occur in the next 7 days. Past, present, and future rainfall. Our future rainfall is what we call QPF, or quantitative precipitation forecasting. I do this for most of Texas, most of New Mexico, southern Colorado, and northern Mexico as well. Yes, we do go across international borders. It's not easy to determine how much rain is falling right now, and we'll be talking more about that as we get into the meat of our presentation. Just a little bit of background about the National Weather Service. We have weather forecast offices in 122 different cities in the United States and its territories. The map on the left that you're looking at shows you how the National Weather Service weather forecast offices are divvied up across the continental United States. You can see from the map on the left that the counties are determined for each WFO. In other words, they're all county-oriented. So a specific county is under the responsibility of a specific WFO. The river forecast centers are different. If you look at the map on the right, there is only 13 of us, and they're not county-oriented. They are river basin-oriented. And so the reason that we are called, for example, the West Gulf River Forecast Center, is that all of our rivers originate in our area, and they all drain directly into the western Gulf of Mexico. Unlike some of the other RFCs where they are part of a much larger river basin, such as the North Central RFC has the headwaters of the Mississippi River, and then the forecasting for the Mississippi actually ends up for the lower Mississippi River Forecast Center down in the New Orleans area. They have responsibility where one RFC hands off the water to another RFC to help make their forecast, so they work together there. And same with the Ohio River Forecast Center. But we're unique in the fact that everything starts and stops in our area and drains directly into the Gulf of Mexico. So none of our main river systems are tributaries of any of the other river systems. But as you can see on the map, there's 13 river forecast centers, and it's all driven by river basins and not counties. Now, within the West Gulf River Forecast Center area, it's a very, very diverse area. Everything that you see inside the black line is a part of our area of responsibility. It covers 402,000 square miles of total area, of which 87,000 square miles of it is in the country of Mexico. The Rio Grande tributaries that help the flow of the Rio Grande that we have to make flood forecasts for actually originates out of the country of Mexico. We have 320 different forecast points on 15 different major river systems. Our furthest most east river makes up the border between Texas and Louisiana. That's the Sabine River. And our furthest most south and west river is the Rio Grande, which actually has its headwaters up in south central Colorado around El Norte and Alamosa, and flows southward, of course, down through much of New Mexico to El Paso. And from El Paso all the way down, it makes up the border between Texas and Mexico. But again, it's a very climatologically diverse area. They get as much as 65 inches of rain per year down in extreme southeast Texas and southwest Louisiana. That's our wettest point. And then you go out into the desert-like areas of southern New Mexico, and you can get as little as 8 inches of rain per year. So it's very diverse. The main thing that we watch in the western United States is the amount of snow that occurs during the late fall, winter, and early spring out in the Rocky Mountain chain of southern Colorado and northern New Mexico. It's because it's the snow melt that occurs in the spring from the mountain snowfalls that determines how much flow actually gets into the Rio Grande. So that in and of itself presents problems of trying to keep track of one part of the hydrologic cycle, and that is how much snow falls in the mountainous regions of the Rio Grande drainage. Once you move down into the western parts of Texas, it is rather desert-like, but then as you get further east and the rainfall increases, it gets very hilly and yet very wet. And so we have the Texas Hill Country where we see rapid river responses. It's a huge flash flood threat and is very rocky terrain. There's a lot of marble-like features in the Texas Hill Country where runoff is very fast of any rainfall that occurs. Then, of course, when you talk about the Gulf Coast itself, you're talking about landfalling hurricanes and tropical storms as a threat. There's also the possibility you could get significant storm surges and coastal flooding as a result. And once you get into North Texas, where we have the populous Dallas-Fort Worth Metroplex, we have a complex reservoir operation in place that is used for water supply, so that in the hot, dry times of summer, we still have drinking water. And so we monitor all of this. We can get prolonged river flooding here when we get a lot of rain. Of late, we've been in a drought, and we haven't had much flooding of late. And Texas has sustained some pretty bad drought-like conditions since the late 2008-2009 time frame. So the main duty of river forecast centers then is to make river flood forecasts. And we have two working groups within our office to accomplish this. One is the one I'm a part of, which is the hydrometeorological operations, where we take care of monitoring past, present, and future precipitation. And we have 3 meteorologists in our office, which are called HAS forecasters. And Weather Service is notorious for our acronyms, and so HAS stands for Hydrometeorological Analysis and Support Forecasters. So the 3 of us that are meteorologists are in charge of monitoring the precipitation for our hydrologic unit. We have 11 hydrologists in our office, and some of which are professional engineers. And they're the ones that actually issue the river data and forecasts and keep track of the water supply based on the information that we give them about the past, present, and future rainfall. One question we do get, since that we have been in a drought lately, is what do we do when it isn't flooding? And the main answer to that is we do a lot of research and development. Unlike the meteorological side of the National Weather Service that has its own environmental modeling center where they're coming up constantly with new weather models like the GFS and other models, we have to do our own modeling in-house. We have the framework of the model, but the actual augmentation of that model to make sure that it will work better for the next flood is actually developed all in-house by our hydrologists. And so that keeps us very busy. So why is flood forecasting so difficult? You know, meteorology has come a long way in its use of weather models to help improve weather forecasting. We haven't quite seen the same kind of success on the flood forecasting side of the house. Well, why is that? Well, one of the big reasons is because of the problems we have in accurately measuring all aspects of the hydrologic cycle. For those who aren't real familiar with the hydrologic cycle, this is a simplified version that you're going to see throughout the presentation of what different aspects of the hydrologic cycle is. We start off on the left with evaporation and transpiration, where vegetation itself, the trees and crops and so forth, give off a certain amount of moisture, which we call transpiration. Evaporation coming, of course, from different types of soils as well as from area rivers and lakes. And then, of course, once the evaporation and evapotranspiration occurs, it goes up into the upper atmosphere, and eventually we have condensation. When the clouds that form get so heavy and so forth, they start dropping their moisture in the form of precipitation here on the right side of the picture. And precipitation can fall in several different forms. In the higher elevations, quite often it's in the form of snowfall, and in the winter, of course, at surface level, it's in the form of snow. At warmer climates and during the summertime, the precipitation generally falls as rain. One of the things then we have to determine is in Colorado and New Mexico, in our area of responsibility, we have to figure out how much of the springtime warmth is going to relate to runoff from snowmelt and get into our area rivers and lakes. And then, of course, if rainfall hits the ground directly, we have the problem of determining surface runoff, or how much of that moisture that's hitting the ground is directly going to run off into rivers and lakes. Now, this would be very simple if we had measurements taken for all these different aspects of the hydrologic cycle. It also would be very simple if the evaporation and the evapotranspiration occurred and it all stayed in one spot. But in reality, what happens is the upper air winds catch the water vapor that has formed, and it literally can blow for hundreds, if not thousands of miles across the globe. See how much water vapor is and evaporate from one spot. We also have to see what the transport of that water vapor is and how it relates to weather and where it's going to precipitate. So one reason why flood forecasting is so difficult is because the amount of water vapor can be measured, but it does move. And so you have to keep track of the movement of that water vapor. But it can be measured. Water vapor coming from evaporation is measured in several different ways. The first way, of course, is by sensors on the ground. As you're probably well aware, we have dew point sensors all over the airports that have what we call ASOS, or Automated Service Observing Systems. And so quite frequently, from land areas at least, we do get a direct measure of the amount of atmospheric moisture in the form of dew point temperature from all over the globe. So that is one way that we start off by sensing how much moisture has been evaporated or has moved into a specific area, at least at the ground level. But we don't stop with the dew point sensors on the ground, but we also send up weather balloons all across the globe. Here's an example of a weather balloon being blown up with a radiosonde package that has a dew point sensor being attached to the bottom. Now, these balloons are launched twice a day from many different locations all across the globe, and then they measure the amount of water vapor that there is in the upper atmosphere. So we have surface weather observing systems and upper air systems. And last but not least, we get a pretty good idea of how the moisture is being transported by using weather satellites. There is one channel or one aspect of the weather satellites that can view the amount of water vapor that is in the atmosphere, and we can loop these weather satellites on the water vapor imagery to see exactly how much moisture is flowing to a specific area. So the transport of water vapor is very important, and since we have a pretty good idea of how much water vapor there is going across the globe, this is a main input into the weather models that help us to forecast precipitation. So the problem, though, really starts beginning on the precipitation side of the hydrologic cycle. This area of evaporation, evapotranspiration, is pretty well measured. The amount of condensation is pretty well modeled in our weather models, but then we don't do so well on the precipitation side. So this is the area that we really need some work on. How much precipitation is actually falling? Well, knowing the precise amounts of precipitation reaching the ground is essential in determining runoff and, in turn, making good river forecasts. If we do not have a good handle on how much precipitation is falling at any one given moment, we don't have a chance of making a real good river flood forecast in real time. And this, by the way, is a picture from down in New Braunfels, Texas. Down on the edge of the Texas Hill Country, this is the Guadalupe River that was in flood after Tropical Storm Hermine back in 2010. Well, how much precipitation is falling? What are the different sensors we use? Well, we talked about on the other side of the hydrologic cycle how dew point sensors are on radiosondes and also on the dew point sensors on the ground. Now we're going to talk about the different sensors we use to try to determine how much precipitation is actually falling. Well, most of our determination nowadays on how much precipitation is reaching the ground is done by using weather radar. The timing and location of rainfall and snowfall from radar is outstanding. It's certainly far better than any of the other sensors that we have. But the radar precipitation estimates can be in considerable error, and we'll talk about why here in just a moment. But let me just cut to the chase and tell you that we also use hourly rain gauges, and what we use those for is to bias our radar estimates higher or lower based upon what the rain gauge data is saying. So we try to compensate for any shortcomings that the radar-based information might give us in terms of precipitation estimation. We also get satellite-derived precipitation estimates. They are used where radar data and gauges do not exist. This is especially true in northern Mexico. So one of your questions that we had going into your registering for the class is, can satellite-derived precipitation estimates be used in helping us to determine how much precipitation is reaching the ground? The answer is yes, but it's not our most reliable or most accurate source of precipitation estimation. So we do get radar estimates of precipitation. Here's a WSR88D sampling a big thunderstorm that's occurring off in the distance. Unfortunately, I wish I could say that the radar precipitation estimates were perfect and we had an absolutely great data set going into our hydrologic model that's telling us exactly how much runoff is going to occur. But radar precipitation estimates can be and often are in considerable error. So then why do we use them? I mean, if they're in considerable error, why do we use them as our baseline products for our precipitation analysis? Well, the bottom line is there's really nothing better than radar. And we're going to talk about the fact that the timing and the location of radar precipitation estimates are really far superior than anything else we've got. And just to show you an example of what a radar precipitation estimate looks like, this is when Hurricane Ike was moving up into Houston. You can see that, yes, it was really not raining in the eye of the storm on that day, but there was significant rainfall occurring on the bands, the banding features that were occurring around the eye. So here are some of the other precipitation sensors we use. Of course, I mentioned radar is listed as number 3. QPE simply stands for quantitative precipitation estimation. You don't need to remember that. But it is going to be used periodically in my presentation so that if you see QPE, that's what we're talking about. There are problems with all the different sensors that we use. Automated rain gauges have problems, and the short of that is that there can be considerable undercatch from automated rain gauges on a windy day, or during a thunderstorm when it's very windy, or during a landfalling hurricane. The precipitation rates can be off. That's simply because when it's raining really, really hard, tipping bucket rain gauges have a problem keeping up with the precipitation rate, and we can get undercatch that way. There's problems with satellite precipitation estimates, and we'll talk a little bit about that. And radar, we'll talk about the different reasons why radar has its problems with estimating rainfall. Well, the first and foremost, one of the problems that we can have with rain gauges, especially automated ones, is something called sighting. Sighting of the rain gauges is critical. You don't want to find a rain gauge that's located directly under a tree, especially if the tree is covered with full vegetation in the summertime. You won't get an accurate amount of rainfall in your gauge if it's not sighted properly. But hopefully, most of the gauges we use, it's not a problem of sighting. It would be some other problem of why we might not get an accurate rainfall reading. I mentioned the wind problem. We'll talk more about that in just a second, and as well as tipping bucket losses from automated gauges. But sighting is important. I one time saw a rain gauge that was sighted right underneath a bridge, and while it looked like it was far enough away from the bridge, we actually saw that there were puddles from a recent rainfall that the puddles were causing spray to go down off the bridge and landing right into the gauge long after the rainfall had actually ended. So sighting is critical. We don't do well in estimating rainfall or snowfall when it's frozen precipitation. That's a problem. That's why some gauges, automated ones, are heated. We do have a problem with automated gauges giving us signal malfunctions that don't communicate properly with us. And, of course, there can be mechanical problems. And sometimes you even find birds like the nests in the top of rain gauges, and that can be some real issues. So there's several different things to take into account with problems with rain gauges. A lot of people like to call rain gauges ground truth, but quite often they are not ground truth. They have their own sets of errors. It's been shown in different studies that if it's raining outside and there's a 10-mile-an-hour wind, you can lose as much as 10% of the rainfall in your gauge. At 15 miles an hour, sometimes it can be as much as a 20% loss of rainfall. Now, if you get up to tropical storm force winds, which is equal to or greater than 39 miles an hour, you sometimes can lose as much as half the amount of rainfall. So our general rule of thumb is expect a 20% error during thunderstorms. And if you have a 1-inch error for every time there's 5 inches of rain. So quite often, even when we have a heavy rainfall reading, its chances are it is too small as well, especially if it's from a windy situation. When I was speaking a moment ago about Tropical Storm Ike, we were having a real problem with our hourly rain gauges, even though they were showing us more than 1 inch of rain per hour. The catch was so low that actual rain gauge readings were closer to 3 to 4 inches per hour in the Houston area. It caused tremendous problems for us, and the fact that we thought that the rain gauges were fairly close, and in fact they were not. And the wind speeds were anywhere from 50 to 70 miles an hour as the rain was falling, which caused the automated gauges to undercatch considerably. Tipping buckets, inside an automated rain gauge, most of the tipping buckets measure 1/100th of an inch per click. But if you have a very intense rainfall, you can get a loss of precipitation when the bucket tips, which takes about a half second. So therefore, if you have a rain rate of 6 inches per hour, which is really significant, but it can happen in the tropical areas especially, to have a zero error, it would require you to hold more than 1/100th of an inch per tip. Some of the newer automated rain gauges now measure in 400ths of an inch to try to compensate for that. So the bottom line is there is no substitute for a manually read rain gauge from an analog gauge in real time. We think that our best rain gauge data we have is when a human observer has read an analog gauge that is well and properly sighted. And so those are the kinds of observers that we love to get observations from in real time if possible. One of the problems we have is quite often when observers, skywarn observers or storm spotters want to call in a rainfall report, they don't give us an actual amount. They'll say, I've got a rain rate going on here of 2 inches per hour. Well, that doesn't help us out. We can look at the radar, and it's already telling us that it's raining hard at a specific location, but the radar does not tell us an exact amount, and that's what we really need. Now, look, changing subjects for a second, we do get satellite precipitation estimates. They are based upon the brightness temperatures in the infrared satellite image. In other words, the colder the cloud tops, it's assumed the heavier the rainfall is that's occurring underneath the clouds. And you can see an example on the right, the corresponding rainfall estimate that we have from the thunderstorms that are occurring, in this case, to the southwest of Houston. You can see that fairly intense rainfall has been measured from this particular satellite image. The problem is if you look at this picture of the thunderstorm, the entire top of the cumulonimbus cloud, or CB cloud, is going to show up as one rainfall rate, but these smaller towering cumulus clouds that are below it are at a much warmer temperature. In other words, the brightness temperatures aren't nearly as cold. So that in satellite precip estimates lead to an overestimate of precipitation being measured from the cirrus clouds, or the blow-off of the cirrus, or the anvil, and we underestimate the warmer cloud top features that are down below. Quite often in tropical storms, the cloud tops are very warm, and it will not show much of heavy rain at all occurring on a satellite. So while we can use satellite, it is our least accurate measure of how much precipitation is really reaching the ground. So let's go back to radar precipitation estimates, since it is our primary mode of estimating rainfall. I want to give just a very brief explanation of how electromagnetic energy, and it sends it out in pulses. And these pulses are very, very fast. The pulses actually go out very short, and then what it does is the radar actually listens for a response. And it's waiting for some type of electromagnetic energy, a much smaller amount of electromagnetic energy to be bounced back to the radar. The longer it takes for the electromagnetic energy to bounce back to the radar antenna determines how far away the target is that is sending back the electromagnetic energy. So, for example, if this thunderstorm in this picture is 40 miles away, it would be a known quantity of distance of how long it would take for that electromagnetic energy to come back from the rain droplets from that thunderstorm to come back and be registered by the radar. Now, what we do from there is, let's say we do get some small amount of energy returned to the radar. It is measured in something called decibels, or something that you might see on a radar screen called dBz. That can go anywhere from 0, meaning there's no return energy, all the way up to maybe above 70, which is indicative of a very large rain droplet or something else that would be very significant. So we call the return power that is measured in decibels Z, or reflectivity. Something has been reflected back to the radar. Now the radar then turns around and assigns a relationship to Z in terms of an hourly rainfall rate, and we call the hourly rainfall rate R. So when reflectivity comes back measured in dBz, we assign it a rainfall rate called R, or the ZR relationship. So that, in short, is how we get our radar precipitation estimates. Now, there's problems with radar precipitation estimates, and we're going to talk a little about that now. Firstly, let's say your radar is located next to a mountain. Well, the electromagnetic energy that has been sent out in pulse form from the radar antenna is going to be beam blocked because of the mountain. Therefore, you might get a good estimate of precipitation between the radar antenna and the mountain, but it can't see anything beyond the mountain. So because of the problem with terrain, you're going to underestimate badly the amount of precipitation on the other side of the mountain range. Also, you have to keep in mind that the radar beam is going out in a straight line. Unfortunately, as you go further and further away from the radar antenna, the Earth actually curves. So as you get further out, your radar beam is further and further and further above the ground level. So as you get further out, you actually can get to a point where your radar beam is overshooting all the clouds and the precipitation. This is what's called range degradation. Now, in systems that are producing rainfall, but the cloud tops are very low, you may not get any rainfall estimation of precipitation beyond a certain range as a result. So that's a problem with radar. This is one of the reasons why the radars are spaced apart by about 150 to 200 miles across the United States to try to compensate for range degradation. We also have something called anomalous propagation on radar. It would be nice if everything that we saw on the radar that looked like precipitation really was. But quite often we will detect anything from migrating birds to bees that may be flying around, and we'll pick up buildings, trees, and wind farms, and all sorts of other things that are targets that are returning reflectivity, but it's not from water droplets. And so we call this anomalous propagation. It's pretty easy to recognize for what it is, and we remove it automatically through our processes at the River Forecast Center so that we're not accumulating precipitation from something that is buildings, trees, and migrating birds. But radar does assume that everything that you see that is reflected back to the antenna is a water droplet in liquid form. And as you quite know, at this time of year, you can get sleet and melted snow that also will be shown on radar. And this is what we'll look up as being what we call bright banding. It looks like it's very, very heavy precipitation, but in fact, we are seeing precipitation as ice form rather than liquid, and that really screws up our ZR relationship, the relationship between the reflected power and what's actually hitting the ground. Also, in thunderstorms in the summertime, they can contain hail, and so we'll have something called hail contamination. The radar electromagnetic energy loves water-coated ice and will return the maximum reflectivities from water-coated ice, whether it be hail or melting snow. And so we will overestimate the amount of precipitation hitting the ground in those situations. There are other times, though, as I mentioned, from beam blockage or other problems of low-level information that we will underestimate the amount of rainfall on radar. Also, we can have inappropriate ZR relationships based upon assumptions made for the drop size diameters in the clouds themselves, and I'll demonstrate this more here in just a second. The radar can be out of calibration. That's not as big a problem as it once was because we do have systems in place on the National Weather Service radars where the change in system calibration is monitored every volume scan. So this can be a problem, but generally is not. And of late, we have retrofitted all the WSR-80D radars in the country to do what's called dual polarization. That's where we send out pulses of electromagnetic energy not only in the horizontal phase, but also in the vertical phase. This has helped us to improve our precipitation estimates, but not in every event. So another one of your questions is do we still have perfect radar precipitation estimates now that dual polarization has been implemented? And the answer is, unfortunately, not. It is better than what we've had before, but it is still not perfect, and not perfect by any means in all different types of weather events. I'm not going to get into the how the Doppler radar uses the dual polarization in this talk because it's very, very complex. I'm just going to explain how some errors can occur in radar precipitation estimation based upon the different assumptions that are made. And one of the assumptions made is that in a sample volume, you have an equal number of rain droplets of one set size. And unfortunately, that doesn't always fit what's really going on in the real atmosphere. There is more sensitivity given to drop diameter than drop density. Here you have two sample volumes on this slide. They're both the same size, about a cubic meter of air. On the sample on your left, you have 729 1-millimeter drops. Now, when the radar comes and samples this, it looks at the drop sizes and says that the amount of return power is 29 dBz's. Now, in the sample on the left, you have but one raindrop, but boy, it's 3 times the size. It is a 3-millimeter raindrop, and so that when the radar comes along and samples it, it also says that the return power is 29 dBz's. Well, in our radar precipitation estimate equations, that means that the reflectivity of these two samples are going to be identical. It's going to tell the River Forecast Center that underneath this cubic meter of air, 9/100ths of an inch of rain is falling. Unfortunately, because you have so many 1-millimeter drops here, your actual rain rate is 22/100ths of an inch. So you've underestimated by radar a factor of 2 and almost 3. About 2.5 times. There's 2.5 times more rainfall occurring here than what you actually would be sampling on radar. And so on the sample on the right, in reality, your actual rain rate is 2/100ths of an inch, and it says it's 9/100ths. So in this case, you've overestimated by a factor of 4. So in this particular case, you can see that you have the same reflectivity, but you have vastly different rain rates. And this is why we bias our radar precipitation estimates in-house. In this situation, hopefully a rain gauge would catch the 22/100ths of an inch, and we would bias the radar up to show something higher than 9/100ths of an inch. And in this situation, hopefully a rain gauge would catch the 2/100ths of an inch, and we were lower the 9/100ths of an inch, something closer to the 2/100ths of an inch. Hopefully that's pretty clear for you to see why we have problems measuring precipitation using radar. Well, now that we've seen that there's deficiencies in all of our precipitation sensors, and how do us hydrometeorologists improve these estimates? And this is where CoCoRaHS starts to come into the whole equation. One of the questions I had asked is that, is there any value in CoCoRaHS rainfall observations when we only get them once a day in our 24-hour readings? And we're going to show you the answer to that question is yes, they are invaluable to us. Well, as forecasters improve the radar precipitation estimates by closely monitoring and quality controlling the hourly rain gauge data, and then we use these hourly rain gauges to further bias the radar precipitation estimates. And so here's the whole goal of what we're after. We use a program in-house called the Multi-Sensor Precipitation Estimator, or MPE program. The main objective of MPE then is to reduce both the aerial mean and the local bias errors in the radar-derived rainfall by using the radars, rain gauges, and satellite precip estimates so that our final best estimate of the rainfall is better than if we had used any one of the single sensors by themselves. So hopefully we're making vast improvements over using any one of the sensors if they had just been by themselves. And prior to 1995, all that the West Gulf RC used in determining the amount of rainfall was by using 24-hour rain gauge data. And that was back before the days that we had CoCoRaHS observers. And it was very, very difficult because it would be very easy to miss a intense rainfall if it didn't occur where there was a rain gauge located. And so that was a huge problem that we used to have. But now we run MPE every hour. We get the radar-based precipitation estimates, and then we bias these radar estimates using the hourly gauges. And we do this by quality controlling all the rain gauge data. It's pretty easy to sense when a rain gauge is malfunctioning, and we can eliminate that from our estimation processes. So we check the radar biases, we recalculate them, we recheck them, and then in a manual step we remove all anomalous propagation, and this becomes our best estimate field. Now, the thing I want you to realize is even after we've gone through all these quality control checks, we've biased the radar, we've added in our own best estimates of precip, we've looked at all the different fields that are available, and when the day is all said and done, these are still estimates. How do we know if our estimates are close, our input into the hydrologic model? How do we know if that precipitation estimate is close? Well, we do a lot of MPE post-analysis. The following morning after it's rained, we do what I like to call Monday morning quarterbacking, where at 7 o'clock in the morning we go back and we use a program in-house called XNav, which accumulates 24 hours worth of our MPE best estimate fields, and it enables us then to put the 24-hour rain gauge data right on top of it so we can do direct comparisons. This happens to be from the 19th of October back in 2006, where we had a very heavy rainfall event down in the Neches River Valley to the northeast of Houston. We can zoom in on our area of interest, and we can slap right on top of our estimates the CoCoRaHS data and also 24-hour readings from other data sources. And then we consider, again, our 24-hour analog or manually read rain gauge data to be our most reliable data set. So you CoCoRaHS observers that are very diligent in making 24-hour rain gauge data, this is how the river forecast centers are using them, and this rain gauge data is invaluable. We can literally point on your gauge, if you had a heavy rainfall reading in the area of concern, and we can tell exactly how much rainfall you observed and what our MPE estimates were at the location of the gauge and also where we placed our cursor and pressed on our cursor. So it gives us a direct comparison between what you observed and what we had estimated from our MPE program. Now, if we should happen to find out that there are several gauges in an area that are reading higher or lower than our original MPE estimates, we can and do go back and adjust the radar-based precipitation estimates up in that area so that we can actually get the input into our hydrologic model to match what the CoCoRaHS rainfall readings are. Just to give you an example of how a CoCoRaHS observation or several CoCoRaHS observations have literally helped us to get it right in real time. We got one particular morning a CoCoRaHS observation out of Ellis County, Texas, which is one county due south of the city of Dallas. This happened to be an observer in May Pearl, 6 west southwest. This individual observer gave us a rainfall reading of 4.5 inches in the last 24 hours. Well, it turns out that our initial MPE estimate for this location was about 2.6 inches. So as you can see, we had only estimated about half the amount of rainfall that the CoCoRaHS observations had shown to have really had fallen. And that's a big problem. And the problem is that in the runoff section, it may have taken 2.5 inches just to wet the soil. But anything above the 2.6 inches going on up to the 4.1 inches could be pure runoff that we would see go directly into the nearby Trinity River. And so we would need to know that to make an accurate flood forecast. So here's what we did. We went in and went back and upped our precipitation estimates in MPE to match the 4.5 inches of rain that the Ellis County observer gave us from near May Pearl, so that we matched out pretty good. And so that enabled us to put this directly into our hydrologic model to get a better estimate of runoff into the Trinity River and allow us to make a flood forecast for it. So the more CoCoRaHS observers we have, the better the chances are that we are going to catch the most intense rainfall. And of course, it's the most intense rainfall that is going to cause main stem river flooding and helps us do our job. Each and every day we produce this table that you're seeing on your screen right now, where here's the Texas CoCoRaHS ID. It tells what the observer from highest to lowest gave us in terms of their observed 24-hour rainfall reading. And then we can compare all of our other fields to what the CoCoRaHS gauge was. So it helps us in a tabular form to directly see how close we matched in MPE to the different CoCoRaHS observers. And this really is a tremendous help to us. So we then, thanks to CoCoRaHS, have a pretty good idea of how much precipitation has fallen in the last 24 hours and allow us to input that into our hydrologic model. So we have a good estimate of rainfall. So is the problem solved? Unfortunately not. And that's because as we get into the last part of the hydrologic cycle, the runoff is not known. And one of the other questions we had asked you before this webinar series is, of the parts of the hydrologic cycle, which ones do we have the most difficulty in actually ascertaining or knowing about? And the answer is actually runoff. And the reason is that there aren't that many ground sensors that measure the amount of moisture in the ground around the country. Now, there are some mesonets, such as up in Oklahoma, where they do have a pretty good handle on how much soil moisture is in the ground at different levels of the ground, going down from surface down to the subsoil. But in general, there is a great lack of determining how much moisture there really is in the soil. So what do hydrologists do? Well, that's what the hydrologic model is intended to do. We simulate the runoff using a hydrologic model. The problem with the model is that the amount of moisture in the ground is not directly measured, so they have to estimate it. Hydrologists use what's called a soil moisture accounting model to assess how much moisture is actually in the ground. So runoff is dependent on how wet the dry the soil is. If the soil is totally saturated and it starts to rain on it, the amount of rain that runs off is going to be 100%. If the ground is very dry, the chances are that there is going to be a lot of the moisture seeping into the ground that will not run off into rivers and lakes, at least not immediately. And it has to wait until the soil gets to the saturation point before it will start to run off. And so runoff is dependent highly on how much moisture there's in the soil. And so we try to account for each and every rainfall event, which makes it even that much more important that we have an accurate measure in each location of how much precipitation actually fell. So once we have determined that, the soil moisture accounting model will actually keep track of how long it has been since the last time it has rained. It'll keep track of the time of year because evapotranspiration is highly dependent on whether it's summer or winter, with summer, of course, having much more evaporation than the wintertime. And all these factors are used to determine the amount of soil moisture in its estimation in the hydrologist soil moisture accounting model. So it's a real problem because we know that once soil saturation occurs and runoff begins, something called a threshold runoff, we then can measure the amount of runoff once it hits the stream gauging network. And that is one of the parts of the hydrologic cycle that we do have a good measure of also, is that there is a good network of rain gauge stage or river stage gauges going up and down the different rivers, thanks to the U.S. Geological Survey, the U.S. Army Corps of Engineers, and other river authorities that have networks of stream gauges out there. So we get all of this data so we can actually see how much water is getting into the rivers. But the key here is we try to make our flood forecasts as it's raining. We'd like to do it even before it starts to rain if we got an accurate handle on how much precipitation is actually going to fall, or a good QPF forecast. But unfortunately, QPF leaves a lot to be desired. It still has a lot of work that needs to be done. So we really wait until the precipitation starts to fall and see where it's rained the heaviest before we make our flood forecast. But if we had a better idea of how much water is actually going to run off and how quick it's going to run off, we could make even better flood forecasts in real time. But again, the CoCoRaHS observers help us out by giving us a 24-hour rainfall so that we can get the amount of precipitation going into the hydrologic models more accurate. So once the water is in the rivers and the lakes and it's in the topsoil, we start the whole cycle all over again, known as the hydrologic cycle. So that's how it all fits together, folks. We really need your rainfall observations badly to help us get an idea of how much surface runoff we're going to see. And with that, this presentation has come to a shocking conclusion. So I will be happy to entertain any questions that you might have. And as Henry mentioned a little while ago, you're to type your questions in, and he's going to read them to me, and hopefully we would be able to come up with some answers. If you would prefer to just email me directly, there's my email address, and I would be happy to talk to you about any of this by way of email. But Henry, for now, I'll turn it back to you.
Thanks, Greg. Boy, this is very interesting stuff. A lot of things on there to soak in. But that was very good. What we'll do is we'll take some questions now. In fact, there's a question that was on there. If the person that was typing in the question had the word gravity in it would retype that one. It fell off our screen here. We'll try to answer that. Here's Lloyd in Palmyra, New York, and he said, what is the expected wind loss for snow as for rain collection? So is there much of a difference?
Not really. It can be the same type of problem. But measuring snow in a gauge is a whole different problem as it is. Obviously, if the gauge is frozen, it's going to show up as 0, or if the top of the orifice of the gauge is clogged, it's not going to show anything but a 0. And we see that a lot when it is snowing out in New Mexico and Colorado. The gauges will actually still be reporting, but will give us 0 readings. Some of the ASOS gauges are heated. They have antifreeze in them, and we will get readings that way. But again, if it's blowing really hard, hopefully we'll have, and you'll see pictures of some of the ASOS rain gauges that actually have got turbines around the edge of it that will help break up the wind current so that the precipitation will fall closer to straight down into the gauge around it. You see that sometimes, but not all the time. So yes, I don't know what the losses would be from snowfall in the gauge, but it would be considerable, I would think, as well.
Yeah, this is Nolan, and snow losses with strong winds can actually come darn close to 90% loss, which means only catching 10% of what's falling in a real blizzard situation. So that's why we strongly recommend doing core samples if you can find a representative location.
Sure. That's very true. So I would say that the losses are even worse with snow than they are with rain and high winds, but both are a problem.
A viewer wants to know how many river forecast centers exist in the country. You went over that earlier. If you could repeat that, and where's the one for the Midwest area? He wanted to know.
There are 12 in the lower 48, plus there's one up in Alaska. The River Forecast Center in Alaska has responsibility for Alaska and the Pacific regions as well. But of the 12 in the lower United States, the office that's in Atlanta, Georgia, or near Atlanta and Peachtree City, Georgia, also has responsibility for San Juan, or in the Puerto Rico area. In the Midwest, there's a River Forecast Center in Minneapolis area, near Chanhassen, Minnesota, and the one for the Missouri Basin is located in Kansas City. And then in the south central part of the country, there's one in Slidell, Louisiana. And if you're thinking of the Ohio River, there's one outside of Cincinnati, Ohio as well.
Thanks, Greg. Here's a question from Kevin, and Kevin wants to know who looks at a storm after it occurs. evaluates it, and estimates its frequency? Do you prepare a depth area duration, a DAD curve, for the storms?
We have a design center in Washington, D.C. as part of the National Weather Service headquarters that develops those, yes. We get the charts that say what the maximum possible precipitation is over different locations at different time intervals from them. I don't think the one in Texas has actually been rewritten for many, many years, but they are working on other parts of the country as time goes on. So it is done by our hydrologic design studies at the Weather Service headquarters.
Thanks, Greg. If anybody else has any questions, go ahead and type them in. Nolan, do you have any questions for Greg, since you're on the call today?
I do. You're talking about soil moisture and the uncertainty of soil moisture, and we certainly see that in our drought monitoring efforts. And recently, well, two things are happening. NASA is going to be launching a new satellite sometime this year, hopefully, regarding to soil moisture estimation from space. But the question has come up, can CoCoRaHS observers take some sort of ground measurement in their own yards or fields that could be useful? And I like the idea. We haven't developed it fully, but do you think CoCoRaHS could be a potential source of soil moisture information that would be useful to river forecast centers?
It's possible. I don't know in what form we would need it in. I know that we see more soil temperatures and soil, observing systems that will measure actual soil temperature at different levels. Whether there's any relationship between that and the amount of moisture in the ground, I'm not exactly sure. But any type of data that we could get would be helpful. I know that they're already, with the current weather satellites and environmental satellites that are in outer space, they're looking at different ways of determining at least the amount of topsoil moisture that is available for drought purposes. But in terms of actually being able to tell what the depth of the moisture is and so forth, it's a little bit more difficult to ascertain using satellite. So that's why we have the hydrologic model. It literally is taking into account the time of year, the type of soil, and the amount of moisture that fell in the last storm and the length of time between storms to try to estimate how much soil moisture there is in the upper part of the soil as well as the lower parts as well.
And then I have a second question. Thanks very much. And that is, where would people go to see the predictions that river forecast centers put out? How do they track that information down on the web?
That's a good question. We have something called the Advanced Hydrologic Prediction Service, and it's available on the web to anybody. The AHAPS pages is water.weather.gov on the internet. Water.weather.gov. Now, one thing that we get asked a lot is, I mentioned the MPE estimates, the hourly estimates of precipitation, and they want us to be able to see if that data is available in real time, and it is. It's available if you would take the water.weather.gov and put a /precip, P-R-E-C-I-P, it would give you the page where you can actually see the last 24 hours of rainfall that we have estimated from any of the river forecast centers, not just ours, but for the whole United States. And then, of course, we archive that data, and we actually have the ability to see, well, how does that compare to normal? What is the percent of normal? Is it above or below normal? It is all in there. And a lot of people are even downloading that data and using it in different engineering studies for rainfall and so forth. But if you just go to water.weather.gov, you also can click and see where our different forecast points are, and you can actually press on any one of those points and see a hydrograph of what we're forecasting in terms of the water at that location.
I just went there on the website, and it's quite incredible, and it's amazing that people, as you look at that product, I highly recommend it. Realize that your rain gauge observations are very likely influencing those forecasts.
Absolutely.
Okay, well, thanks. Here's another question. Larry writes in, is the official rain gauge that reporters use more accurate if the top funnel and the inner gauge is removed?
Are they talking about the standard 4-inch rain gauge?
I guess the CoCoRaHS gauge is probably.
Boy, Henry could answer that one. I mean, Nolan could answer that one better than I probably could. But
I'll speak to that. In the winter, absolutely. With the funnel and inner tube in, if you're getting snow, you're going to miss moisture that would otherwise collect in the gauge. That's why we always recommend take the funnel and inner tube out for winter measurements when you're going to be below freezing, and then bring that sample in to melt and measure it. For summer, you're actually much better with the funnel and inner tube in, because it, number one, focuses the moisture into the calibrated inner tube and allows us to measure that very accurately. But and then it keeps water from evaporating that might otherwise evaporate. But what's interesting is if we have a lot of hail, hail can bounce out of the funnel, and we have a few observers who will set up gauges side by side, one with the funnel in and one with the funnel out. Most times they measure similarly, but occasionally if there's a lot of hail, the funnel removed will give you a better measurement. So that's probably more information than you wanted to know, but it's things we definitely think about here at CoCoRaHS.
Very good.
Thanks. Here's Hugh writing in, wants to know, are flood forecasts more accurate in the Southwest in areas where there's a lot of rock and therefore soil moisture is removed from the calculations?
It can be, but again, all flood forecasts are as good as us knowing how much rainfall is actually occurring in real time to generate that flood, especially when the runoff is so fast. When you have a rocky soil, you're almost totally taking the hydrologic model out of the equation, because if the rainfall runoff relationship is nearly 1-to-1, then it's almost 100% that the rain that's falling is going to run into the river and run off and go downstream. So that's where we really need to know in real time how much rain has actually occurred and what the rain rate has been. We've seen this over and over again in the mountainous areas. Nolan can probably talk all day about different heavy rainfall events that occurred in the Colorado Rockies that have led to tremendous flash floods in rocky terrain, where no hydrologic model is going to be able to accurately tell you exactly how high the floodwaters are going to get. But there is a relationship between the amount of rain and the rainfall rate and how high the river would probably go. After we see how much rain actually fell and then what the actual river crest at, then we can calibrate what model we can use to know that if we had that kind of rain in that location again, this is how high the river has gotten in the past. We can calibrate the model appropriately. So a lot of what we do with the amount of runoff is we calibrate the model based on past rainfall events. Once we know how much rain occurred and how high the river got, then we can model accordingly. So I hope that answers the question. It's very difficult to be able to do in the western United States, especially since in the mountainous areas, that's where your radar precipitation estimates are your least reliable. So.
Thanks, Craig. Craig writes, he says, would you please restate the websites where one can download temperature and rainfall data, preferably records that are 50 years or greater? And well, we can post that on our WeatherTalk page if you want to give that to me afterwards.
The one that I was just mentioning again is the word water.weather.gov. and then
water.weather.gov. Okay.
yeah, and from there you can go /AHPS to actually see river stage and forecast information, or you can go /precip and you can see our rainfall precipitation estimates. If the person on the webinar was more interested in the actual design studies of maximum probable precipitation and so forth, that's a totally different website that I could supply to you later on, if that's what it was that they were after.
And this is
Okay,
Nolan.
great.
For retrieval of basic climate information, that's another website as well, and we'll look that up and post that later.
Yeah, appreciate that.
Okay, here's Michael in Colorado wanted to know if you have a recommendation for a resource to learn how rivers converge, basically where they begin and where they end. Is there something on the web or a book that can describe this more geography-wise?
I'm not sure. I think the best thing they could do, again, is to go to the water.weather.gov site. We have decision support pages that actually will show what the basin outlines are and the deviations between the basins. It may not be in the type of detail that the person is after there in Colorado, but it might be a start. Interestingly enough, that the delineation of the Rio Grande headwaters in south central Colorado, you basically can draw a line along all the high peaks going from the San Juan Mountains all the way up and over to south of Buena Vista, Colorado, and then back down on the other side of Alamosa, between Alamosa and Pueblo and Colorado Springs, and then southward on the Santa de Cristo peaks. And everything inside that line that you just drew, those snow melt, is going to come inward, and that's what forms the Rio Grande. Anything that forms west of there as snow melt is going to go in the Colorado Basin. Anything east of the Santa de Cristo is going to go in the Arkansas River. So it's all based upon elevation as to each drop of rain, each flake of snow, where's it actually going to end up in terms of water. It's all quite often based on elevation. So if you've got a topographic map, that's a good place to start of what river is starting and stopping in a specific place based on that.
And this is Nolan. I cannot remember the website, but the U.S. Geological Survey has divided up every basin into what they call hydrologic units, and there's probably a online map that shows these hydrologic areas, which are all different dimensions of river basins, starting at the scale of the Mississippi, then down to the Missouri, and then to tributaries to the Missouri, like the South Platte and the Yellowstone, etc., and then on right down to the locals, tiny little drainages in your own communities. And likewise, CoCoRaHS, we're getting ever so close to having a new mapping system where we will be able to let you overlay drainage basins, river basins on the CoCoRaHS rainfall map, so you can see what rain is falling in what basin. That's going to be a really fun addition when we have that ready.
Yeah, that's great. One question I had, and I hear a lot as the North Texas Regional CoCoRaHS Coordinator, is there in development any kind of a application to access CoCoRaHS, to especially enter your observation using, say, an Apple iPhone app or anything like that?
Well, we already have an Android app. It's not a really fancy one, but hundreds of people are using the Android app, and we have the ingredients in place for the iPhone app. It's not done yet, and unfortunately we have about 3 or 4 other tasks we have to complete first, but it's definitely on our list, so don't worry, that it will come eventually.
Yeah, I've been telling everybody, yeah, just keep doing it the way you're doing it for now, it'll come. So I was just
Thank you.
Greg, here's one. A gentleman in Canada up near Winnipeg says the altitude gradient from the Big Stone country to Lake Winnipeg is only about 100 feet. How does river flow with this small gradient affect flood forecasting? So can you go into that a little bit?
Well, actually what we try to do is model not only the flow of water on the top of the soil, but also down at the lower levels as well, because there's always some kind of a base flow of water occurring even if the topsoil is dry. And so quite often, even in the middle of a drought, you'll see some moisture still going down a river channel, and that is actually coming from subsurface moisture called base flow that is actually going through there. So just depending, again, on what this gentleman has up in the Winnipeg area, he could be either seeing topsoil moisture from melted glacier type activity or snow during the winter, or he could actually see moisture that has been stored for years through aquifers and so forth that is actually still moving underground and getting and seeping its way into rivers and lakes. We try to account for both in our hydrologic model as best we can.
And the Red River, which of course flows from the northern U.S. into Winnipeg, has a remarkably low gradient. So that's always, and it flows from where the snows melt first in the lower elevate or lower latitudes in the U.S. and then flows back into the areas that are still melting closer to Winnipeg and beyond. And that's why we've had some incredible floods and forecast challenges on that river, and some of your other big Canadian rivers that end up heading towards Hudson Bay.
Yep.
We just got a message in that somebody's suggesting a national atlas for the up to downstream flow depictions of rivers. I will post that on our website. We'll put that one up there.
Yep.
We're getting close to the end of our broadcast for today, so we'll take another question or two. And I guess here's one here. What do you consider a good estimate for river flooding? One plus or minus a foot? Are the predictions biased to be lower or higher than expected? Kevin writes.
Okay. Well, even though you may see it in terms of a stage that is measured in feet, we actually think of it in terms of flow. And so 1 foot difference at one gauge may equal a certain amount of cubic feet per second going by a point where in another river system, a foot difference may be something drastically more or less. We have broken down all of our forecast points into what's called an action stage, minor flood, moderate flood, and major flood, and of course record flood categories. We try to hit the proper category. It's impossible to get it to the nearest inch. We try to get it, to the nearest half a foot or so forth in terms of our flood forecast. Usually if we're within a range of a foot, we're feeling pretty good down here in Texas. But it's also, we are always thinking in terms of flow. We want to get the proper amount of flood flow. And we want to make sure that we get it into proper categories, because the key to flooding is getting the people who are downstream from the flood waters to be able to take the proper action based upon how high the waters are actually going to get. And so we look very closely at the actual amount of flow as opposed to just looking simply at the stage.
Thanks, Greg. Here's our last question of the day, and the gentleman Craig here would like to know, has climate change made it more difficult to accurately predict runoff?
No, it really hasn't. The bigger problem we have is urbanization. The more the cities get larger, the more people there are to draw down the amount of water that's in the lakes, the more people that there are to use up the subsoil moisture and aquifers and stuff like that. That has much more of an impact on runoff than climate change itself. I mean, obviously, if you get less rainfall or more rainfall, that's going to have an impact. I'm not saying that. But what affects the amount of runoff our hydrologic model calculates is that it makes certain assumptions about soil type and soil usage and so forth. But the larger the cities get, the more runoff you see from concrete, parking lots, more highways and so forth, that actually speeds up the amount of runoff than what we might ordinarily take into account. And so that's why we have to recalibrate our river after every rainfall event that hopefully is going to catch some of those problems that we have with urbanization.
Well, thank you very much, Greg, for this presentation today and for the questions you were able to answer. If we didn't get to your question today, Greg will try to follow up with you in the next couple of weeks. We'll send him a list of those questions. And again, we appreciate you taking the time out of your busy day to be with us for one of our CoCoRaHS Weather Talk webinars. Folks out there, please join us for our next CoCoRaHS Weather Talk webinar. That'll be on Thursday, February 20th. Ryan Boyles, the North Carolina State climatologist, will talk about what a climatologist does. What do climatologists do? So you'll want to go ahead and register for that. We'll have that information up on the website and also in our message of the day coming up shortly. Before you guys leave today, please take the survey at the end of the webinar. That'll come up as you sign out. It'll be really helpful to us here. So on behalf of the CoCoRaHS staff, we again want to thank Greg for this great presentation. We want to wish you guys a happy day or a good day out there, and have a good week ahead, and we'll catch you next time. Take care. Have a great day.